Okay, it's good to be here for the second time to talk about Babylon and code reflection. I was trying to find a nice picture to represent the project, and I actually found one which is astonishingly accurate. There's this artist, Shirin, who did this Babel tower in the desert in Iran, and it's a reflective tower. Excellent. And it's a Babel tower. Excellent too. It's amazing. It spins around according to light conditions and the temperature conditions in the desert. So I thought that was amazing. And I did actually email her and ask her for permission to actually show this. All right. So I'm going to give a bit of a status update, explain something pretty important to Babylon, which is called code models, and then go into a bit of a sandwich, really. I'm going to talk about how we obtain code models and how we identify methods to get code models out and reflect over them. And I'm going to talk a bit about transformation at a high level. And I'm going to go back and talk about reflecting on lambdas like this. So I'll start sort of ramping it up as we go along. So last year I presented on this. This is the first time we disclosed what we were working on this. And in between then, we've created a project, we've open sourced the code reflection in January, and we've made significant progress on the implementation of this and design of this as we go forward. And we published a bunch of articles on code reflection. My goal on these articles was to sort of inspire people, not to necessarily go deep down into the design of it, to inspire people of what might be possible so that people can do their own things on what might be possible and surprise us. Because I think this project is, if people get involved in it, they're going to surprise us with what they can do. And lastly, we also open sourced quite recently what we call HAT, the Heterogeneous Accelerator Toolkit. I'll be talking about this later, which we're trying to use code reflection and Panama to leverage GPUs. Code on Java, compile down to GPUs. So what is code reflection? It's really an enhancement to Java reflection. So Java reflection currently gives access to fields and methods, but it doesn't go deep. We can't get access to the code in methods. The idea of code reflection is we broaden the access or deepen the access to code in identified method bodies and Lambda bodies. So John Rose calls this cracking open Lambdas. So we like to crack open a Lambda or crack open a method and get access to the code and give access to this at compile time and runtime. At the moment, we're focusing on the runtime aspects, but we want to bring it backwards so we can get access to the same information at both compile time and runtime. And this primarily enables support of what we call foreign programming models via transformation. So the idea is that you may have your Java program and you can translate it to another program. That translation may not preserve Java program meaning, but that's okay, that's up to you. We are not changing Java program meaning here. We're not changing the Java specifications to support GPUs or to support auto-differentiation. That's up to the transformation to do it. And the reflected code is represented symbolically, and we call this a code model. And a code model just is nothing magical here. It just consists of instances of Java classes. We call code elements and items, and they're arranged in a mutable tree structure. And compiler developers will be very familiar with this kind of thing. And that tree structure, we're trying to design this so it's suitable for analysis and transformation by other Java programs. And the challenge here is to get the design of this model just right to support a whole range of transformations and analysis. That's the real challenge. So we can't just focus on one vertical. We've got to focus on a broad set of use cases. And this code model design is heavily inspired by LLVM and more heavily inspired by the MLIR initiatives in LLVM. And with the code models, we need to build them, we need to traverse them, and we need to transform them. So there'll be APIs around all of those three things. So the code model design is actually fairly simple. Again, compiler developers will be very familiar with this. It's a code model contains operations, bodies, and blocks that form a tree. Anyone familiar with that on C2, Graal, and all these types of LLVM? Not a surprise there. It may be a surprise if you're coming from the Java source side. This is not an AST-like representation. It's more of a compiler representation. But you can use it for analysis like you use it for ASTs as well. It's not stopping you from doing a broad set of use cases if you think about it carefully. It's a tree structure, so an operation contains 0 or more bodies, a body contains 1 or more blocks, and a block contains a sequence of one or more operations. That's the tree structure in essence. And blocks and operations can declare values. A block can declare 0 or more block parameter values, and an operation can declare an operation result. And this is where we model phi nodes. Phi nodes are modeled as block parameters, and this is what was done in Swift intermediate representation. This is what is done in MLAR representation. I think if we introduce code models and had the notion of phi nodes directly in it, we would lose half the Java developers in the room or more. So we can model it in a way that looks similar to functions or methods in a way. Values can only be assigned once on declaration, so it's in static single assignment form. I always get it wrong. Is it static single or single static? I get them mixed up. And an operation can use values as operands. So only after values have been declared and they denominate. So, and a value has a type. So in fact, I can fit it all on this slide, although I'm sort of speaking quite fast. It means it's quite compact and I think quite accessible. So the blocks in the body, they form an interconnected graph that we call a control flow graph. And the last operation, the body can jump to another block within the same body, and that forms your graph. And that should be familiar with compiler developers as well. Values are also interconnected, and they form different graphs. So values can form expression graphs or use graphs. So the relationship between an operation result and its operands are edges in an expression graph. And the relationship between a value and its uses form a use graph. And so you can choose to, depending on what analysis you want to do, traverse the control flow graph or traverse the data dependencies as expressions, which sort of go up the tree, and uses which sort of go down the tree. And this is a sort of a snapshot in IntelliJ of this API I just talked about. It almost writes itself. The creativity is in design, and the API is just derived from the design here. All the creativity in the API is working out how to build and traverse and transform these models. What we want these models to be is immutable. And so building and transforming these has challenges that you wouldn't do if they were mutable models. So we have a hierarchy here. At the top is a code item, and there's 9 classes all related here. So when we talk about the tree here, they're instances of code elements. So a code element is a block, body, or an operation in the tree. That's it. An op and a type element are unsealed. So this is where we can extend from type element and op, and this is where we add behavior to code models. So this is just the meta form, if you like, and it doesn't do anything except provide these structures I said before. And the way we provide behavior is extend from these, and that's how we start to model Java program behavior, by extending from operation and type element to introduce specific behaviors for Java language constructs and their types. So what are Java code models? Well, a Java code model is a symbolic description of a Java program. So it will contain operations and types modeling Java program behavior and arranged to preserve Java program meaning. So language declarations, expressions, statements, and specific behaviors are modeled as classes extending from operation. And then denotable Java types are modeled as classes extending from type elements, a value type. And we call the set of operations and types that model some kind of program behavior as a dialect, and that's copied from MLAR. You see in MLAR, there's sort of types and operations in the group together to get a dialect, like a GPU dialect or a SIMD dialect or something like that. And so we can say that a Java dialect models Java program behavior. So modeling-wise, these code models are somewhere between an abstract syntax tree and bytecode. They sort of sit somewhere between there. And so the idea is these things should be easier to analyze and transform. It's sort of just the right amount, the Goldilocks thing. Sometimes I think cynically, we win here if we make everyone just a little bit unhappy, because I've seen when people come to this, they come with their own expectations and they think, I want an AST-like thing. You're not going to get an AST-like. And someone comes, I want a bytecode. You're not going to get that, but you're going to get something in the middle that is actually, hopefully you're going to be productive using, and hopefully it's going to be easy for you to transform into your domain that is of interest to you. So this model preserves more information than bytecode, but with less surface syntax details of the AST. So we strip out all of the details that aren't important and keep it to something that's relevant to the code. And the important thing here is we can standardize modeling and access. We can't bytecode access is not standardized. The AST of the compiler is not fully standardized either. So let's get into how we identify methods that can be reflected over. So we identify a method by annotating it. So we got a very simple method here, purely because we can fit it on the slide. An add method adds two numbers together. If we want to reflect over this and get access to its content, the code, we annotate it with @code reflection, like so. And then we can access the code model using reflection APIs we have today. So we've got a method add. We use the methods, we use Java reflection. We're all familiar today to get access to the method object, the reflective method object of add. And the first line there, and then if we want to get the code model, we call the add method.getCodeModel on there, and it returns an optional because it's partial, because not all methods can be reflected over, because if we don't annotate it, we don't have the code model available for it. So what's going on here? So we take what's going on in the compiler here. So we take our Java source, the Java compiler parses and verifies it, produces an AST, does attribution on it to make sure it's all type correct. If it's all type correct, then it passes the compiler. Well, in normal cases, that AST will be translated to bytecode, and then we will store that bytecode in a class file. When we annotate it, we also go off to the side here, and we translate identified code into a Java code model, and then we also store that into the class file. So we're storing two things into the class file here. And this is a partial transformation, in part because code, if you don't have the annotation on it, won't work, but also we're not sure how much of Java source we can fully translate into code models. There's certain restrictions where we may not be able to translate all Java language constructs. However, we're working to try and translate as much as possible. So what happens? What does the class file look like when we have this add method annotated with code reflection? Well, we've got to store something in the class file. So this is the prototype storage, what we're doing, and I've highlighted stuff in yellow here of relevance, of interest. So we've got to store this code model we generated by the compiler, and we've got to serialize it somehow and stuff it in a class file. So the simplest thing to do is serialize it as a string and store it in a string field. So that's pretty hacky, but it works for now. So we can see a highlight here on the constant number 54. There's this strange string called thunk with an add and some location like that. That's our serialized code model. And then we have a hash 57, which is the name of the field we use to say this is the name of the field where we're storing the string of the serialized form of this code model. And then we see a static initializer at the end there, and we're doing a put static 55. And if you follow it back, 55 refers to 7 and 56, and 56 refers to 57, which is this field name, and you can see it refer to the content too. So that's how we're doing it right now. It's pretty straightforward. I'll talk later, it might not be the way we end up doing this. So just a detour, you may be wondering that string I showed you there, well, what the heck is it? Well, we could extract this text string from the class file, or we could directly convert it to an operation to a human-readable string. The two are identical. So the API allows you to print out that text string we stored in the class file. So if we get our code model, we can convert it to text and we can print it out. What we're doing, what the compiler's doing, exactly the same thing. It's just producing the text and storing it into the class file. And this is the actual code model as in serialized form there. I'm not going to go too deep into this, but this is a great way to debug and test code models. In the past, we've sort of been over-rotated on this in some ways, and trying to think of this as the primary form of code models, but it's not. The primary form of code models is the runtime instances in memory, and this is a serialized form. And it may be possible to serialize out, but not deserialize in all cases. So we're not going to lean on this as a form and standardize it, but we're going to use it as a way to debug and test code models. So we try not to over-rotate on the serialized form here. But I think it's fairly readable. Also, we have location information in here as well. So when debugging, we can, if we're going to generate bytecode from it or other kinds of code, we can embed location information all the way down. So in a summary here, what's going on? The source compiler is translating AST nodes of the add method to a code model, and it converts that code model to a text string and assigns that string to a synthetic field in the class file. And at runtime, we access the synthetic field to obtain the text string and then parse that text string to produce a code model back. Fairly straightforward. So there's a bunch of issues with this. So one is we're probably misusing annotations. Annotations are not meant to sort of change language semantics. But in this case, it kind of arguably is, although it's sort of on the threshold. Compilation may fail. Maybe we can't represent all code, so we have to produce a compilation error. Maybe what we really need here is a keyword. Not sure yet, but we might. Say reflectable keyword or something like that. But annotations are great for prototyping. And I think the other thing is storing the text string is a synthetic field in a synthetic field is really convenient for prototyping, but I don't think this is a good final solution. One is I don't want to standardize that serialized form at all. It's just going to create horrible bugs later on and a minefield of stuff. Serialization is a minefield regardless. I do not want to add to that. So I think it's best to avoid standardizing that and also avoid standardizing the field name mangling going on here as well. This is a prototype. So this text form is primarily intended for debugging and testing. Let's stick to that and not try and sort of expand what we do here with that. So an alternative solution we have sort of a rough prototype for is to transform the code model into a code model that builds itself. That makes sense? It's kind of nice. It's got a nice sort of circularity to it. We can do this because we can transform it using the transformation API to generate code that uses the builder API. And then we translate that code model to bytecode, and we stuff it in the class file as a method, and then we reference it through an attribute. And that means we don't need to standardize anything except the APIs we already have. And that will work cross-platform across, say, Eclipse or the Java compiler. So I think we probably have to lean into this way, or at least explore this way, and see if this has legs to it. I think it has other advantages I'll mention later on as well. And I don't think it's going to be any larger, actually, because of the constant pool. The constant pool will intern all the strings, and it's initially I bought this solution thinking this is going to create huge amounts of bytecode for the description of the code model, but it doesn't, I don't think, because of the way the constant pool shares information. I think it'll be pretty efficient. So as also, you may notice there's two representations of code in the class file now. There's the bytecode and the code model. I was wondering, can we unify these, perhaps? What if we have only the code model, and when you need the bytecode, we dynamically transform and produce the bytecode on demand? Maybe we can do that. Maybe we can use John Rose's Mindy, method invoke dynamic. And the Mindy points to a bootstrap with the code model. And when we initially want to do something with it, Mindy kicks in and produces the bytecode for the method. The bytecode and code models can get out of sync as well. But that can happen anyway. So I don't see there's not much we can do about that. Of course, if we unify, that solves that problem, but you can still monkey around with the class file and change the contents at any point in time if there's a man in the middle. I think we also need to validate these code models. So when they're loaded from a class, we need to make sure they're actually correct. This is vexing me a little bit on how to do this, but I think if we lean into the code model transformed into a builder of code models using the API will enforce the structural constraints we have already on the building models. So that will keep that in check, I think. Although we may have to deal with the annoying things. Usually in these cases, we throw errors rather than runtime exceptions. But I think we can work around that. So leaning into building code models, transforming code models that build themselves is probably a good move because we can solve at least part of the validation problem as well. So I'm going to flip now and talk a bit about transformations of bytecode. transformations of code models. The first thing is, the natural thing to do is we can generate bytecode from code models. I think that's something that's a given we have to do. So we take a code model, and before we translate it to bytecode, first, the next step is we could lower the code model into a lowered form. So we can replace structures with interconnected basic blocks. If you like, we can have the code models at the top level can capture the nested structure of code, which is what MLIR does. It captures the nested structure of code. We capture the nested structure of code as a tree, and we can collapse that into a set of interconnected basic blocks, lowering, like so, and we can replace the variables we model in pure SSA form with the values they use and store, and we keep it lower. And that, depending on what you want to do, you may want to use the higher model or the lower model for your use case. In the case for bytecode, it's easier first to lower it and then generate bytecode from that. And as we go through this lowering process, we preserve the Java program meaning. So the bytecode coming out of here is a conformant Java program from the source. Once we get the bytecode, well, we could lift it back up. And we could go back down, and hopefully it's stable at this point, while preserving Java program meaning. So we've been exploring lifting bytecode as well. And Adam Satone has been doing an absolute excellent job generating bytecode from code models and lifting them back up and going back down and seeing if it's stable. And we've almost got this working. We're testing against about 30,000 methods in Java base, lifting them up, going down, lifting them up. And we're pretty close to getting this working and preserving. Actually, it's quite tricky to determine if you preserve the Java program meaning as you go up and down like this. It's a challenge, but this round trip is almost working over a wide set of bytecodes. Particularly challenging because we always get surprised at what Java-C can produce. I think it's also useful to lift up from bytecode, not just as a proof of concept that we can do this in code models, but because there's class files out there, and we should make it easier to analyze those as well. So we can go down to bytecode, we can lift up, go around. Well, we can do other stuff. We could transform a code model and generate its differentiation through automatic differentiation. And once we generate the code model there, we can generate bytecode and then run it. So there's a sort of a classic kind of Java to Java transformations we can do with code models. And for autodiff, it may be easier to use a lowered code model rather than the higher code model. And in this case, we're going from Java to Java. Arguably, autodiff is a foreign programming model. In a sense, it's not specified by the Java language specification. It knows nothing about auto-differentiation. And yet we can implement a library using code models to translate. This is where it gets more interesting. If you go off to the left instead, we can do more interesting things. So at a high-level code model, what we could do is we could translate that, and we could generate OpenCL C or CUDA C, C99 code. We'll talk about that at a high level later. We could lower it, and we could generate SPIR-V or PTX. SPIR-V is the bytecode specified by the Kronos group in OpenCL, and PTX is NVIDIA's sort of lower level interoperable assembly code. And we'll have a talk about this, about SPIR-V, coming after me. And we have prototypes for PTX in the HAT, the Heterogeneous Accelerator Toolkit we've been looking at too. So we got options. The idea is that the code model is flexible enough at different levels for you to choose your interchange point out or your translation point out to the various areas you want to support. Now, these are the Java program to a foreign programming model, but they may not preserve Java program meaning. So if we're going to go off to generate OpenCL C code, it may be restricted in what types of code we can generate and what we can run on it, because it's not going to maybe support the managed runtime of Java, maybe no GC on it, and so forth like that. But we can also do other things here. Well, we could go from the high-level code model, and maybe we generate NVVM IR and use the compiler toolchain then on NVIDIA to generate the PTX. So NVVM IR is, I believe, a specification of the LLVM initiative to represent GPU programs in the LLVM bitcode. And so we can choose to use the NNVR compiler toolchain, and it can generate either, I don't know if it can generate SPIRV, but it can generate PTX code, like so. And the advantage of doing that is the NVVM compiler may have more optimizations in it than our ability to generate PTX from code models itself. So you leverage a compiler of your choice for the optimizations you want to get, and you don't have to implement those optimizations yourself. So the idea is you can interchange to other formats and leverage all these interesting compilers out there today, and you do not have to do the work yourself. The work is to translate the code models to the form that you pass to the compiler to do the job for you. There's even more interesting stuff here. You could translate the code model to a Triton code model. Triton is an initiative by OpenAI to allow you to write CUDA code in Python in an easier way than writing CUDA itself, and more performant as well. And so I implemented a prototype of a Triton-like code model transformer that in theory you could then convert to Triton MLIR and throw it at the Triton MLIR compiler to generate your PTX code as well. And maybe there'll be some interesting talk about that after me as well. And the idea is, again, to show interchange. So we can support a Triton code model for GPUs. We could support a sort of say, grid or ND range model for GPUs as well. But there's other things we can do as well. We could take the code model at a high level and translate it to an SQL statement. I'm still waiting for volunteers to explore this to see if we can actually do it. I think it's possible. Or, again, volunteers, please. I really think we can do this. We can translate code models to ONNX models. And so we can do training in Java through this kind of thing. And this is similar, if you're familiar with ONNX, ONNX is a format for representing machine learning models, initiative developed by Microsoft. And then you can define a model, execute it for training, or execute it for inference. I think we can represent, Java code can represent these models, and we can extract the ONNX model from the Java code. And this is what ONNX script in Python does. And we can do exactly the same thing here. I think we just need some people, some innovative and clever people to try this out and to prove that this can be done. I think it can. So there's another one here. Anyone who likes Lambda calculus, you could translate the code model to administrative normal form. Why? Because I want to see it can be done, but maybe there's compilers out there that take inputs like this that can do useful analysis on code. So if you're a fan of a continuous passing style or ANF, this is interesting. And I think this can be done too, and it doesn't look like a hard transformation. We found a paper that shows how you can do this from SSA form, and I believe we can actually do it. So someone is actually trying to do this. Ian Graves is trying to look at this right now. And it's a theoretical thing, but I think an interesting thing to prove it out. So here's some transformation examples. Very high level, I'm not going to go into the details of the API here. So we have a code model. We got, say, from our add method. If we want to lower it, we call transformation on it, and we pass in an implementation of a transformer. In this case, it's a lowering transformer, which takes all the high-level nested structures and translates it into an interconnected graph of basic blocks. And we can implement this, and we can actually do it all in one pass for many Java language constructs, patterns, switches, try-statements, and so forth. Once we've got the lowered model, we can do a further transformation and translate it into pure SSA and get rid of all the local variables. And then from that point, you can choose which point you want to operate on in terms of how you want to process the code model. So the point is there's choices here. The code model is not going to define one thing. It's going to define many things that you can use depending on how you want to translate into your domain. We can generate bytecode. We can first lower it, and then we can use the bytecode generator of the lowered model and get a method handle out from which we can invoke. Or we could lift. So we can generate the lowered code model, we can generate the bytecode class data, and then we can lift the model up, lift the bytecode back up to a code model, like so. Or you could get your class data from somewhere else. So here's an example of a forward auto-differentiation. It's a very rough prototype written as a test in the prototype in Babylon code base. So we take our code model, a function we want to differentiate. In this case, it's a function that takes two independent variables, x and y. We lower it and we SSA transform it. Again, it's code models in, code models out. Code models are immutable. We get code model in, we translate it to another code model, and so forth. So the bet is that leaning in on functional, immutable is better than leaning in on mutable. There's trade-offs to this, but I think in the long run it will pay off. So in the expression, in the differentiation, we're doing forward differentiation here. So we need to differentiate between first with x, with respect to x, and then with respect to y, sorry. And so what we do is we get a block parameter for the value of x. We forward differentiate partial diff with respect to that as a transformation. And then we do some expression elimination just to clean up. So we don't when you do auto diff like this, it usually generates some expressions that are redundant. But rather than merging that transformation into the partial diff transformation, it's a separate one. Often I find that when doing these kinds of transformations, it's better to do one thing in sequence rather than try and munge it together. So this is how we do it here. We do it with respect to x and respect to y. We get a method handle for each. And then those two method handles correspond to the gradient function. And if you want to look at the code is linked here. Okay, back on to Lambda. So I talked a bit about methods. I talked a bit about translation at a high level. And now I'm going to talk about how we identify code to be reflected over in Lambda expressions. So one way we can do this is we can identify by target typing using intersection types. Anyone familiar with serialization will know we're copying exactly what serialization does, but we're not going to be constrained by serialization. So we can, I'm using the term quotable here, but please don't think this is metaprogramming. I think this is probably the wrong term. And maybe it should be called reflectable or something like that. We're not trying to add metaprogramming into Java. Okay. So we intersection type here, we say it's of quotable, and then we get the usual double binary operator out on the left-hand side there. So if you want to get access to the code model of this, we have to cast it back to a quotable and then ask it for what it's quoted. So from a quotable, we get a quoted, and from a quoted, we get an op. Right, so that's the way I'm currently doing it. We'll talk about pros and cons later. So the other way to do it is to extend your functional interface with quotable instead. And then you don't need to do the cast. Same thing though, you get the quoted out from the quotable and you get the op that's reflected, the model of the Lambda expression from the quoted. So as I said, quotable behaves similarly to serializable. So quoted encapsulates the sort of Lambda expression's code model, but also it encapsulates any of the captured variables as well. What if a Lambda captured a variable? What do we do there? So again, we can, these lambdas can capture variables just like normal Lambda expressions can. And we can access the code model, but we can also access the captured arguments. So what are the captured arguments? The captured arguments are a map of symbolic value to runtime value. So value here is a code item, and it represents a symbolic value in the code model. And the object represents the runtime value that was used, the value of cap here. So the captured values can be applied when the model is processed. And so the model is static and the captured values are dynamic. And also note that no code outside the Lambda expression is captured. So we're not going to go and try and reflect over code that people didn't ask for permission for. So how do we do this? This is a little bit more complex, and I'd like to thank Maurizio for working out how to do this. It's the first stage of doing this. We're going to get better at it. So what we do is we lean into invoke dynamic using the alt meta factory. And so, what we see on the bottom is a bootstrap method, the alt meta factory here. And it's adding some additional flags to say, hey, this is a quotable lambda, take interest in this. And we're referencing, again, a static field where the lambda's code model is actually stored as extra information. And we actually, at the moment, we're also duplicating the list of the captured arguments on the stack because we kept them separate for reasons of complexity, but I hope we can collapse those later on. So at the moment we're duplicating, keeping them separate because of ordering differences and analysis and so forth, but we'll get there to collapse it. So the idea is we lean into augmented array, just like serializable does too. So what is the code model that's actually stored into the class file? Well, it's actually a little different from the code model we saw with the method. And what's going on is we see the lambda there. You can see it's nested in something else. The lambda is the add method, we can see there. We wrap it around a quoted, and we wrap it around a function. So what's going on here is we need to support captures. The captures are represented as the function's arguments at the top. We see %0 double, that represents a capture. And we quote the lambda. And so the interpreted form of this function produces the instance of the code model that we need. And so we just run it through the alt meta factor just runs it through the interpreter, and bang, we got our code model, and bang, we got our captured values. Now, it's not very efficient, but it works, and there's ways to optimize this in the future. But it also has a nice sort of circularity to it as well. So what about method references? Well, they're modeled as desugared lambdas. We thought initially we were modeling method references directly as operations, and that produced some complexities. And we thought, well, this is more syntactic sugar from the perspective of a code model. So we generate the lambda expression that calls the method that we reference instead. But the two are identical here. If we want to reflect over the method reference and the call to the method, it generates the same code models. So if we have a method reference here, we've got a call to a method. What if, as I show here, we're reflecting over double, the add method adding two doubles. We're not going to, the lambda method reference is not going to return the code model of the add method. It's going to return a code model that calls the add method. So what if we want to trampoline to the add code model itself? Well, first of all, we can get the code model of the lambda, and then we can ask it, are you method reference-like? The lambda op is the op modeling lambda expressions. We can ask it, did you come from something that looks like a method reference? And we can, there's a method called method reference, it returns an optional that gives you the invoke operation if that is true. And from the invoke operation, we can get the invoke descriptor and we can resolve it to the method, Java lang reflect method object. And from there, we can get a code model as we've shown before. So we can sort of hop and trampoline on. So we can leverage reflection, we're enhancing reflection, but also reusing reflection as well. So here's something more interesting is, well, we got two methods, M and N both reflectable, and M calls N and N calls M. And what if we wanted to get the code models for these things? Well, you can start from M and traverse its code model and trampoline through to N, and then traverse its code model and trampoline through to M, and you can build up a module of functions representing these. And it's a very simple transformation. So I can take M, I can input it to write a transformation and build up a module of all of the sort of call graph, if you like, of all the functions, all the methods, and how they call each other. And this is actually useful for the GPU work as well, because if you're going to write code that you want to reflect over, you don't want to write it in one big method. You want to write it in lots of, maybe, you want to write it normally how you'd write good code. And you want to slap sort of annotations on. It may be we'll choose later the scoping of annotations. At the moment, we're only identifying each method, and you have to annotate each method you want to reflect. I don't know if we should expand the scope to say all methods in a class are reflectable. But you can do these transformations like this and build up a sort of module of functions that are all reflected over and all interrelated. So here's another one we're a little unsure about. It's called structural target typing. So the target lambda expression, we can, instead of making it quotable, we can directly target it to quoted instead. And to do that, we have to specify the types and names of the variables of the parameters of the lambda expression. You can still capture, like so forth, but actually there is no bytecode generated for this at all. It doesn't make sense. It's totally symbolic. And that's possibly going a little too far, don't know yet, in terms of capabilities. But if you don't want to deal with functional interfaces all the time, you want to deal with more generic stuff, hey, I want to accept any quoted coming into me. I do not want to define 10 different functional interfaces, quotable functional interfaces. This is another way of doing it. This is actually useful. I said I didn't want to talk about metaprogramming, but there is another way we can kind of get splicing kind of stuff in a way. If we rename quoted to reflectable, we can still use quotable or quoted snippets like this to generate, rather than when you're building code models, you want to use a compiler as much as possible because it can build them for you. And so rather than writing code to build models, sometimes you just want a little snippet of code and you want to inline it in an existing code model. And this is the way you can use quoted. Instead of building the code to generate the model, you can get the compiler to do it for a quoted, and then you can inline the quoted into your model. And that's my version of splicing. So there's a couple of issues here with the expression, identification, and access of lambdas here. Same issues regarding code model storage. We noted that captured argument list is duplicated. We think we can solve this. There's also accessing quoted via quotable. Perhaps quotable should be a pure marker interface, and we appeal to reflection to get access to the model of something that's quotable instead. And I think we need to think different names here to avoid the metaprogramming trap. It's maybe reflectable and reflectable lambda. But as I note, quoting is a more general concept to code models. So if you noticed in the serialized form of the lambda that was stored in the class file, you notice I'm using a quoted op. So the concept of quoting in code models is important for modeling the lambdas. And so we use quoted to say the behavior of quoted means return me the model that I'm encapsulated inside here. Do not run me effectively. So I don't know if there's a commonality between serializable and quotable. They're awfully similar. Is there any merging to be done? Is it worth merging? I don't know yet. I need to think about it. But they both trigger introspection of lambda expressions in different ways. Both kinds of lambda proxy expose the captured arguments. So serialized lambda is to serializable as quotable is to quoted respect. So maybe there's a way to common the abstraction, or maybe we try not to tinker around too much with serializable stuff because it's always a pain to do so. I don't know. The thing is that people were using serialized lambda before to crack open lambdas, but now you should be using code reflection when it's ready to do that instead. So here's something interesting that will help explain the GPU stuff that I'm going to talk about later. So here's a kind of pattern. I call it a reflective two-layered dispatch. So we have a quotable consumer. We have a class called layer one. We have a static method on layer one called dispatch that accepts a quotable consumer of layer one. And we have an instance method called dispatch that accepts a quotable consumer of layer two. And then there's this method called test dispatch here. Layer one calls a static dispatch. It passes in a lambda. That lambda is reflected over, and that lambda may encapsulate a particular programming model. And of course, it can call methods inside there. As I've shown you, you can trampoline to methods to group them all together of all the reflected code. But then we can dispatch through the instance method another Lambda that sort of encapsulates another kind of programming model, a layer 2 kind of programming model, sort of closed over in the Lambda. So we're closing over twice reflectively. And this is kind of how the heterogeneous accelerator toolkit does its modeling for GPU code. The host compute program is layer 1, and one or more kernels is layer 2. So we're leaning into that model for the GPU stuff. So I hope to explain that better later, because I'm confused people. Maybe I'm confusing people a bit here. But hopefully keep that in your head for the one but next talk. All right, what's the time? Okay, so there's a lot left unsaid here. There's like 5 hours of content we could talk about. Maybe next time we can talk about modeling of Java language constructs and how we do that. The JLS will want to specify what the compiler must do for identifying source and generating code models, accessing them, and so forth like that. That's a big, big area, how we model stuff. And the JVMS will want to specify what the runtime must do to access and validate these code models. So we've still got a lot of work to do here, especially around specification when we're ready to do so, once we know we got the right thing. I didn't talk really about APIs much. I showed you a bit for code models. On the code model structure, I showed you a bit. I didn't show you much about the operations and how we're modeling Java and the arrangement and all the building, traversing, and transforming you can do. So if you're interested, I encourage you to look at the test cases in Babylon and look at the examples there. And there's a whole bunch of useful analysis and transformations I showed you as a high level of. And I think one thing I'm really waiting for and excited about is once we get user-declared patterns or member patterns, we'll be able to lean into that quite heavily in terms of our API design. And at the moment, it's a little clunky. A lot of transformations rely on pattern matching. And once we get this sort of, how should I say, pattern matching on a rocket pack, we will be able to, how should I say, design our APIs better. And that's it. Any questions?
For generated class files, is the class file validator guaranteed to run for a legal transformation? And if it is, does that mean the transformation correctly reflects Java semantics?
If I got that correct, trying to sort of paraphrase it, you're saying when you validate a class file, will there be transformations happening for that class file?
No, I'm asking, given a transformation, is it only a legal transformation if the class file validator passes?
No, you can, just like it will be valid according to the code model structure. So when you build code models, it will correctly ensure that the relationship structure is correct. And so if it isn't correct, it will throw an error. So it's not like class file validation, but you can think of it as code model validation in that respect. So while building code models, you can only build code models that are structurally correct. You could build them that are semantically incorrect, of course, because you can put any forms of operations that represent code in there, but it should always be structurally correct. As Charlie, at the back there.
This looks like fun stuff. I'll lean into this one too. The one thing I didn't see up here is representation of, say, method handles and Lambda forms. That would obviously be very interesting to us because the vast majority of the magic that happens within a dynamic language is happening on the other side of that invoked dynamic. So ideally, what I would see is we could build a code model of, say, a Ruby method that has some open points on it. And then as we fill those in with method handles and call other things, then we get a better model of the entire system. Is that also a consideration for future work on this?
Do you mean changing Lambda forms to use code models, or?
Well, being able to take the Lambda forms and get a code model out of them. so that I can have a code model of the code that I've generated for a Ruby method, and also any invoke dynamic, any method handle chains I've created would be part of that.
So instead, creating a code model for the method handle call chain of a method handle, that in theory is possible. We have discussed it, but we haven't done anything around that yet. I'm not sure if we will, but it actually is reasonable to think about that, because the method handle structure you're building up is effectively something that's compiled later. It's just Lambda forms for bytecode. But if you could access reflectively the code model of that Lambda form, then you can merge those two code models together and deal with it uniformly. Yep. Yep. Any more questions? Nope. Okay, thank you. Oh, sorry. There is a question here. I missed Chen. Do you want to wait for the microphone?
So just one more. Just curious, do you foresee the possibility of code models taking over like Java decompilers, simply because how code models can be like bytecode can be converted back to lower code models, and code models maybe like, I mean, there's maybe like extra lifting that we can convert like lower code models into Java source code. Do you see that possibility?
I certainly see if we can prove out the lifting, and it's really works well for everything. I think that's going to help people reverse engineer bytecode, because it's hard. Fernflower does heroics here in IntelliJ, and this will give you the first step to do that, both for more powerful analysis as well. So I think that will really help. Going one level up back to source code is even harder. That's what Fernflower does. I think we'll stop at the lower code model and let in the community see if there's anyone heroic in the community who wants to lift it up. But from the GPU point, because we're coming down, we don't need to lift up. So from the GPU side, if we want to generate source code that's not Java source code, OpenCL C99, we don't have to lift up. So it's easier for us in that regard. Yeah, thank you. I think we're good. Okay, thanks a lot.